Today I'm going to look at relativity from its natural starting point, which is the electromagnetic field. Now, the fundamental elements of electricity and magnetism are charges and moving charges. So, between any two charged particles, there is a force given by this equation, and then the electric field due to a charge is the force per unit charge at any point outside of that charge. So E is F over Q. And then the first of Maxwell's equations is Gauss's law, which says that the integral, or the flux, of E over this area is equal to the charge enclosed. Now, the basic concept, the physical source of a magnetic field is a charged particle moving with respect to a charged electron moving with respect to a stationary or a fixed positive charge, or electron moving with respect to the nucleus in a line, and the magnetic field arising from that is given by the right-hand rule. The current is the direction of Q and V, and you wrap it around, and that your thumb points in the direction of V, and use the right-hand rule, and your fingers point in the direction of the magnetic field created by the charged particle moving with respect to that particle, that charged positive nucleus. So, in general, or the more general case of that is a current, which consists of charges moving charges moving with respect to the fixed positive charges, or moving electrons moving with respect to the fixed positive nuclei in the wire. And in that case, the right-hand rule, and that all of these little magnetic field generators create a finite magnetic field B, and the right-hand rule gives the direction of B, and you can calculate B. B is calculated as a constant times the current divided by the radius. The generalization of this leads to Ampere's law, which says that the integral, or the circulation of B around a closed loop, is equal to the integral of the current density, or the flux of the current, the flux of the current across that area, where J is negative charges moving with respect to positive charges. It's not just the flow of electrons. It's electrons moving with respect to positive charges. Now, another example of a magnetic field generated on an atomic scale, if I have an electron circulating around a positive charge, then the electron is cutting the electric field as it goes around and generating a magnetic field which is continuous around the which generates a magnetic field which is wrapped around the path of the electron. So here's the magnetic field at any instant here. And I need a better diagram to show, but the electron moving with respect to the electric field generates a magnet, which is a magnetic field, which is that's the best I can do to describe it. Now, since B, the magnetic field, as you can see here and here and here, the magnetic field is continuous. It doesn't, like an electric field, end or start on a charge. The integral of B dot dA equals 0, which is the magnetic equivalent of Gauss's law, and that says that all the magnetic fields going into an enclosed area all have to leave. They don't end anywhere in that enclosed area on some magnetic pole. Then we have a charged particle moving in an electric field experiences a force F equal Q V cross B, and that leads to an explanation for Faraday's experiment, which is basically a circuit with one moving element. The circuit is between a north and a south pole, so it's in a magnetic field. And if one element of the circuit is movable, if you move that element, then you generate a current or an electromotive force in that circuit. Or in general, that says, the generalization of that says that the integral of E dot dl is equal to d phi dt, where this is the wire, this is the magnetic flux flowing through the wire, and it's generating an electric field E, and integral E dot dl is d phi dt, where phi is the magnetic flux through enclosed by that wire, and it's integral B dot dA. Now, one thing I just noticed here, in Ampere's law, I left out a correction factor for the case where the current, the current may be accumulating in a capacitor, so the current stops there, but you still have current, you still have a magnetic field. The correction factor is taken care of. I'm not getting into the whole theory of electromagnetic fields here. All right. So the summary of electromagnetism is charges exerting forces on each other, an electric field E, which is a force per unit charge, and a magnetic field generated by an electron moving with respect to a positive charge, or cutting electric fields. An electron moving by itself doesn't do anything. It's always the electron moving with respect to the electric field that generates the magnetic field B. Now, there's an interesting question that arises in that regard. There seems to be that this, if you look at, do you have a Kleenex? It's my wife for a Kleenex after a moment. If you look at, that's all right, sir. No. Oh, I'm just going to blow my nose here. Excuse me for 1 sec. I'm not doing this damn thing over here. All right. If you consider, in many textbooks, you see that an electric field a magnetic field is calculated for a moving charged particle. So it's just, you have a charged particle going at a velocity v, and the magnetic field is calculated for that charged particle. But it's not a charged particle just moving by itself. And to check that out, two things occurred to me. The first was, what if I have a charged, say, plastic disc with a lot of electrons in it, and I spin it very fast with an electric motor. Now I have I have this situation here, a charge circulating. So I have a circulating. Wait, where do I have the circulating charge? Here I have a circulating charge, and so I should generate a magnetic field. So out of curiosity, I go to and I Google magnetic field due to rotating charge, and there's a YouTube video, and there's a couple of references to that subject, and they all do the calculation. Sure, you can calculate it, but the amazing thing is nobody ever just take a rotating disc, charge it, then spin it at high speed. Take a disc, charge it, spin it at high speed, and then hold a compass near the disc. Does it move? Is there a magnetic field? Why won't anybody do that? Then the other thing that occurred to me was, if you look at a cathode ray tube where you have a positive and a positive a positive disc and a negative disc. The positive disc has a slot in it. The negative disc is heated. There's a voltage put between them. The positive disc sucks electrons off of the negative disc, and they shoot through the slit in the anode, and you have a ray, and the result is what are called cathode rays. So here's a flow of electrons by themselves. So if electrons flowing by themselves generate a magnetic field, that it's the easiest thing in the world to just take a magnet, a a compass and hold it near the cathode. I can't find any reference to that. So, all right, that's, okay. So my point is that of this whole business is that all electric E&M is due to the action of charges with respect to each other. And this is where relativity just goes into, in my opinion, into Never Never Land, where relativity says that all E&M is due to charges moving with respect to the observer, which to me makes no sense whatsoever. But so for example, if according to relativity, special theory of relativity, if I have an electromagnetic wave moving at a velocity v, whatever that means, v with respect to what, but anyhow, an observer moving with respect to v0, he sees the velocity of the electromagnetic wave as c, speed of light, no matter what v0 is. Whereas in reality, if I have an antenna, then the antenna generates, the antenna sends out an electromagnetic waves that have a velocity, I'll call them photons, a velocity with respect to the antenna of c. So that means if an observer is moving with respect to the antenna at velocity z with respect to a, this observer sees v0 with respect to a, this observer sees c minus, which is the velocity of p with respect to a, minus the velocity of 0 with o with respect to a. Now, the thing that really bothered me about the whole controversy over the speed of light that took place at the turn of the 19th to around the turn from the 19th to the 20th century, everybody was amazed that Maxwell's equation predicted the speed of light to be c. And then the question arose, well, is that velocity c in an absolute reference frame, in other words, with respect to an ether, or is it relative? But nobody asked, where did this light come from? What was the source of the light? Where did it? How does that enter into the equation? The equation the equation for the speed of light is given by these two equations here. This is the general del squared E equal partial squared E partial T squared del squared M equal mu 0 epsilon 0 partial M, permittivity and permeability, permeability. Well, to solve that, it's not just the solution to the equation, but there are boundary conditions and initial conditions. Why didn't anybody ever consider them? Be that, if they had, they would have realized that the solution to this is a speed c with respect to the source, and I'll show that in a minute. Now, all right, so to test this, the theory that just looking at the speed of light in space without considering where it came from, the question was, is it an absolute speed or not? So that's the Michelson-Morley experiment was devised to show that, and it came up with the conclusion that the speed of light, that there was no ether, and that the speed of light was not absolute, and the speed and the results of the experiment were very easily explained with the speed of light being relative to its source. And now I'll show a really nice example that occurred to me. Suppose I have a positive nucleus, and I have electron oscillating up and down next to that nucleus. Well, if that electron is oscillating up and down, at this point, if it's close, it has a force pointing toward the nucleus and an electric field F over Q pointing in that direction. Then it comes down, as it comes down here, it's right next to it, and there is no component in the positive direction. Then it comes down here, and now the electric field is pointing in the opposite direction. So as this oscillates, the electric field oscillates well, at this point you don't know what it does. The electric field oscillates. at the same time, and 90 degrees out of phase with that oscillation, when the electron is cutting through the electric field next to the positive charge, it creates a magnetic field, which is a maximum here, and at this point and this point where the velocity goes to, the velocity is a max here, and out here, where the velocity is zero, the magnetic field is zero. So now, at the same time, however, when the electric field is a max, the max magnetic field is zero, so that the usual picture of a photon or a light, electromagnetic field being in phase, according to this model, they should be 90 degrees out of phase. When E is a maximum, velocity is zero, and M is zero. So this is the the electric field. That's the magnetic field, 90 degrees to it and out of phase with it. Okay, so this is the electron oscillating with respect to theta. Now, the question is, what happens to the electric and magnetic fields once they've been generated? Where do they go? So that question is answered by the wave equation, Maxwell's waves equation, which he determined as, for the electric field, del squared E is mu 0 epsilon 0 partial squared E partial T squared, and del squared M is mu 0 epsilon 0 partial squared M partial T squared. And now the problem with that is, this is a three-dimensional problem because it should be radiating in all directions. However, if you take the point of view that the oscillating electron emits a stream of photons, then instead of emitting electric and magnetic fields in all directions, it's emitting a stream of photons. Then what you're dealing with a one-dimensional wave equation, and that situation you can look at exactly. So now, in that case, if I just have a stream of photons, I have for E, partial squared E partial x squared is 1 over v squared partial squared E partial t squared. And the most general solution to that is E, and you look that up, and I'm not going to discuss, is E is equal to f of x minus vt. All right, now you have an initial condition that has to be satisfied and a boundary condition that has to be satisfied. If I set t equal to 0, then E is, due to this oscillating electron, is a cosine function. So f of x, when t is equal to 0, is E0 cosine of kx. So that E is E0 cosine k f of x minus vt, which is x minus vt. And that has the boundary condition. You notice, if x is equal to 0, then E is, at x equals 0, at that boundary condition, the electron is oscillating up and down. And that's the complete exact solution for the electric field of the photon, and it's exactly the same thing for the magnetic field because it's given by this. The only difference is that the magnetic field is at right angles to the electric field. How can you see that? If the electron is going up, then the current is up, and then the magnetic field is in this direction, perpendicular to the electric field. Okay, and out of phase by 90 degrees as shown here. So that shows that the speed of light, if you take into account the boundary conditions, which you have to if you're solving a wave, if you're basing your observations and your conclusions on a wave equation, well, then you have to, the wave equation has initial conditions and boundary conditions. So as far as I'm concerned, this proves that the speed of light is relative to its source, and which is confirmed by the Michelson-Morley experiment. The speed of light being relative to the source explains perfectly the Michelson-Morley experiment. No matter what orientation you have in space for the Michelson-Morley experiment, there's no phase difference for the two beams that go at 90-degree direction in the Michelson-Morley. Now, you do have the Sagnac experiment, and that appeared to say that the velocity of light was absolute, However, I did a separate video, and I think I'll do another one being a little more specific on it. The speed of light being relative to its source also explains the Sagnac experiment. So everything comes together. This notion of the velocity of light being the same for any observer just makes no sense to me. Now, I think I'll add a couple of remarks and implications of this concept on the next blackboard. Thank you. In part 2, I'm going to consider light from the viewpoint of relative speed and relativity. Relative speed is really also called the ballistic theory of light. And I can illustrate real briefly the difference. If I have a moving reference frame and I fire a bullet in this frame, it's going to have a speed c in this frame, the velocity of the bullet with respect to the pistol, or the photon with respect to the emitter. And in this frame, which is stationary, the speed of the bullet is going to be v plus c. On the other hand, if I have a photon moving at speed c in the moving frame, that the speed of the photon measured in the stationary frame is going to be exactly the same. That is going to be the same. That's relativity, and this is the ballistic theory, which says that the speed of light is constant with respect to the source, which says that the speed of light is measured the same in every reference frame. To begin with, I'm going to consider a radioactive particle that has ejected a radioactive nucleus, which has ejected a particle P, and from the viewpoint of an observer on the nucleus, the velocity of P is Vp with respect to the nucleus. On the other hand, from the viewpoint of an observer on the particle, the nucleus is receding at a velocity Vn with respect to P, where these two both have the same magnet. Now imagine that I have a positive nucleus, an electron oscillating up and down, creating an electromagnetic field, an oscillating electromagnetic field at the origin. Now, what happens to that field as time goes on? According to Maxwell's equation, it propagates through space with a velocity or a speed c with respect to the source. So if I'm at the origin or at the nucleus, I see the front of the wave moving at a speed Vp with respect to n equal to c. On the other hand, if I'm an observer on the particle, then what I see is the same thing that the observer saw at the origin. I see this electromagnetic field moving up and down, and I see the origin, or the nucleus, or the nucleus n, moving away with a speed Vn with respect to P equal to c. Now, this was not the fundamental problem that physicists from the roughly end of the 19th century, even until today, have and had, is that they look at light just as a beam of light traversing through space. They see an area of space and they see light moving across the space without considering what the origin is. In other words, without considering what the initial conditions were and what the boundary conditions were. And it's initial boundary conditions which determine the speed of light relative to the source. And from that point of view, the Michelson-Morley experiment is trivial because the light has a speed c with respect to source, so the result is going to be no interference. However, that caused a lot of difficulty and was easily resolved with the relative speed of light. So now I'm going to consider some of the implications of relativity. The fundamental concepts that arise from and that are used in the theory of relativity are simultaneity, time dilation, and Lorentz contraction. As for simultaneity, I could never really feel right with the explanations I saw on YouTube and on the internet and Google. There was just something missing. It wasn't clear. It wasn't specific. So what I've done is outlined three possible versions of simultaneity. For the first, if you assume that c is constant with respect to the source, I'm going to have a train. This is Einstein's train with a passenger sitting in the middle, and at some instant, the passenger is opposite a stationary passenger on the ground, and lightning strikes at each end. So if you assume that c is constant with respect to source, then the passenger sees the same speed of light approaching her, and she concludes that the lightning strike is simultaneously, whereas the observer on the ground sees a speed of c plus v on to his left, c minus v to his right, and he concludes that it's different. Now, in the same situation, if you assume that c is absolute, see, from the same situation, you conclude, if you assume c is absolute, then the passenger in the train sees light coming at her with a speed c minus v, and coming from the other end at a speed c plus v. The observer on the ground sees a speed c from both directions, so that the passenger concludes, so that the observer on the ground concludes the strikes were simultaneously. And finally, for relativity, both the passenger and the observer on the ground see this light approaching them with speed c from either direction, so they conclude that the lightning strikes were simultaneous. Right, now I'm going to consider time dilation. Imagine a truck moving with velocity v, and there's an observer inside the truck, and a light is flashed on the ceiling, and as far as the observer is concerned, the light, in the photon travels straight down at a speed c, and so the time he measures is delta t bar is equal to h over c. On the other hand, an observer on the ground sees the initial flash at this point, and then sees the light hit this point, but this point now, by the time the light has gotten here, this point has moved the distance v delta t, so that the path of the light to the observer on the ground is this distance here, and it's assumed that the light to the observer on the ground also has speed c, in which case delta t is this distance divided by c, or h squared plus v delta t squared over c. And from these two equations, you get the relation between delta t, the observed time interval in the truck, and by the observer on the ground. In reality, since the speed of light is constant with respect to source, that the light has a speed c heading down, which was its velocity with respect to source. It also has a component v to the right, which is the velocity of the truck. So the actual velocity that the person on the ground sees is the square root of c squared plus v squared, and the actual time is the vertical component c, and that time is h over c. So the times are the same. For Lorentz contraction, we imagine a vehicle moving with speed v, an observer on the vehicle who's going to measure length by looking at the time it takes for a flash of light to go from the front to the back. And another observer is going to measure the length of the train by looking at the time it takes for the same flash, by looking at the time it takes that flash of light to travel from the beginning to the end and back again. So for the observer on the moving with the train, delta t bar is 2 L bar over c. For the observer on the ground watching the train, the time to get from one end to the other going forward, c delta t1, is the distance the light beam travels, which is L, plus in the time it gets to the end, there's an additional distance it has to travel, v delta t1. And the same applies in the other direction, except that as it gets to the end here, this time the end has moved up, so c delta t2 is L minus v delta t2. I'm a little fast on this because these are standard calculations. Right, then if you solve it, you get that L bar is equal to this equation here. When you solve it, you also have to use this equation and that equation, which says that the stationary observer, it says to the observer on the ground, the boxcar appears shorter. The moving boxcar, the observer on the ground, obviously, the moving boxcar appears shorter. I put a question here: is shorter? I'm going to ask a question based on that. Suppose I have two cars of exactly the same length at rest, and they each have a light bulb at the end and contacts coming down from and up from the light bulbs. So that if these contacts touch the light bulb's flash. So now imagine the situation that this car is moving at a speed v, and in that case, I'm going to go off that. In that case, at the instant the car are both aligned up about their center point, and there's an observer on the center. This length is going to appear shorter to that observer. Now the question is, this length appears shorter to the observer. Will the contacts touch? So the upper car appears shorter to observer. Are the contacts touching? That's my question, really. All right. Some miscellaneous observations that I've seen on YouTube. One is an example of I have a current I and a magnetic field generated by that current, and a particle V moving at speed, and a particle moving at speed V. So the force exerted on that particle is QV cross B. That's trivial, straightforward, E&M. However, the point was made that if an observer is moving with respect to the charge, then they see that the velocity of the charge as zero, and therefore there is no force on that charge. And so that F equals QV, B, V is zero, so they conclude that F is zero. However, the correction was made by a relativistic argument involving the Lorentz contraction of particles moving with... I couldn't follow the argument. I totally lost any argument. However, that is really academic. The only thing that matters is the velocity of the particle, or the charge, with respect to the magnetic field. So in this case, the observer sees that the magnetic field is moving away from him with a velocity v, so then he concludes that there's a force on the particle, on the charged particle, of QV, Q with respect to B cross B. The final example is of charged particles, two bars with stationary charged particles, and to observe a stationary with respect to the bars, there's a force of repulsion equal to kq squared over d squared. On the other hand, to an observer running at speed v with respect to the bars, he observes, according to this, he observes a current in these bars. Well, that's not according to that, but the observer running observes a current in these bars, so he concludes that there's a force of repulsion between the bars equal to k I squared over d, which is the formula for the repulsion of equally directed currents. Now, the question is, finishing off with another question, does the state, what actually happens to these bars? Do they stay still, or do they vary as this speed varies? It seems like, according to this, if I'm standing next to these bars and somebody runs past me, they're going to see a current which is going to cause the bars to separate. So I leave that as a question, and that finishes part two. Finally, I would like to thank my wife who directed and produced these videos.
And I take no responsibility for the correctness of the content.
Okay, thank you, Mother. And thank you for watching. Okay.